Types of stresses and strains. So first of all, we'll look on what is a stress. The stress is the force of resistance per unit area offered by a body against a deformation is known as stress. So load is the external force acting on the body. It is applied on the body while the stress induced in the material. If the resistance offered by the member against a deformation and the applied force and load are equal, then the loaded member is in equilibrium. So resisting force is applied force, applied load. So stress is denoted by sigma. So mathematically stress is sigma equals to force upon cross-sectional area. So force we denote it as P or F. Stress is sigma, A is area. So it's nothing but the force. So what are the force applied? So the resisting force or resistance applied from the body to that force is known as stress. So per unit area is known as stress. So it is given by sigma. The symbol for stress is sigma. So once again, so very important, stress is force applied per unit cross-sectional. Cross-sectional means the cutoff, the cross-sectional area. So next, how is this stress measured or unit of stress? So if the force, as we know that force is measured or expressed in terms of newtons, N, and area of cross-section or area, simply area is measured in terms of millimeter square, square, that is, or sometimes meter square also. Then the unit of stress is force by area, so it is Newton per square. The unit of stress is Newton per square. So similarly, then again, if the force applied is in newtons and the area if it is in meter square, then the unit of stress is Newton per meter square. So Newton per meter square. And as we know from physics, kilo is represented by K, mega, kilo means 10 raised to 3, term 10 raised to power 10 raised to 3 is called as kilo, or 1000 is called as kilo. It is represented by K, small k, mega. So mega means 10 raised to 6 is represented by capital M. Giga means 10 raised to 9, it is represented by capital G. Tera means 10 raised to 12, it is represented by capital T. 1 kilonewton means 10 raised to 3 Newton, that is 1000 Newton. 1 mega Newton means 10 raised to 6 means 10 raised to 6 means that is Newtons. 1 giga Newton means 10 raised to 9 Newtons, that is 1 giga Newton equals to 10 raised to 9 Newtons. 1 Newton per meter square is also called as 1 Pascal, or 1 PA. Pascal is called as PA. 10 raised to 6 Newton per square, 10 raised to Newton per meter square is nothing but is equals to 1 Newton per meter square. 1 Newton per meter square is nothing but Pascal. So 1 mega Pascal. So 10 raised to 6 Newton per meter square, or 1 Newton per mega Newton per meter square is 1 mega Pascal. 10 raised to 9 Newton per meter square, or is 1 giga Newton per meter square, is 1 giga Pascal. So stress can be expressed in terms of 1 Newton per meter square, or 10 raised to 6 Newton per millimeter square, or 1 mega Newton per meter square, or 1 MPa. These all are 1. Now strain. So when the body is subject to external force, there is a change in dimension of the body. This change in dimension of the body is called deformation or elongation. Sometimes the ratio of change in dimension of the body to the original dimension of the body is known as strain. The strain is dimensionless and is denoted by epsilon or E. So mathematical strain is change in dimension of the body or deformation of the original body of the dimension of the body. So this dimension can be any dimension, length, breadth or height. So to that of original length, breadth of height, so that ratio is called as the strain. It has no units, there is unitless quantity. It is given by epsilon, divided by epsilon. Now, types of stress. So types of stress. So there are different types of stress. So they are normal stress. In normal stress, we have two stresses, substresses. That is tensile stress and compressive stress. So tensile stress means a pulling stress. Compressive stress means a pushing or compressing stress. Second one is shear stress, also called as tangential stress. Third is a bearing stress. Fourth is bending stress. Fifth is torsional or twisting stress. So when the strains are tensile strain, compressive strain, shear strain, volumetric strain, and superficial strain. So normal stress. So we'll discuss the normal stress, that is tensile and shear stress. So there are two types of normal stress. They are tensile and compressive stress. So first, the tensile stress. So when a body or section is subject to two equal and opposite pulls, as it tends to pull apart the particles of the material, causing extension in the direction of application of load, then the load is called as the tensile load. The corresponding stress induced in this is known as tensile stress. As you can see in the figure 1.4, the load P is pulling in both opposite directions, and the resisting force P dash is being applied. So this resisting force P dash is the tensile load, and the area corresponding area to that and the stress induced is called as tensile stress. As tensile stress is given by sigma equals to same as load by area, resisting force upon cross sectional area. So this is the tensile stress. When pulling occurs, a tensile stress is induced in the body or material. Same tensile strain, when the body or bar is subject to two equal pulls, tensile load, it causes extension, increase in length in the bar and direction of load. The ratio of increase in length to the original length of the bar is known as tensile strain. Tensile strain is extension per, also known as, is defined as extension per unit length. So tensile strain, so here as you can see in the figure 1.5, so the original length of the bar is AB, that is, it is given by the length L, and P is the tensile force being pulled in both directions. Now after pulling, the bar extends by a small amount, that is delta L, so A to C. So A to C is the final length, AB is the original length. So therefore tensile strain is given by increase in length of the bar, that is delta L upon original length of the bar, that is L. So tensile strain is epsilon A equals to, as you know, strain is given by epsilon E equals to delta L by L. Now compressive stress. So when a body or section is subject to two equal opposite pushes, earlier it was pull, now it is pushes. It tends to push the particles of the materials nearer, causing shortening of the direction. Then the load is called as compressive load. The corresponding stress is known as compressive stress. As you show in the figure, the load P is pushing the element in both directions. So the element is trying to resist this force, and the stress induced in that element because of this force is called as compressive stress. So it is compressive stress nothing but resisting force upon cross-sectional area, that is compressive stress sigma equals to P by A. P is a resisting force, A is the area. So compressive strain. So when a body is subject to two equal opposite pushes, it causes shortening or decrease in length of the bar. The direction of application of load, the ratio of decrease in length to original length is known as compressive strain. The compressive strain is shortening per unit length. As you can see in the figure 1.7, so P is trying to compress the original, the section AB. After reducing, it has become to AC. After compressing, it has reduced to AC. So from L, it has decreased to decreased by a small amount, delta L. So shortening, that is compressive strain, is shortening in the bar upon original length of the bar. So formula, so compressive strain epsilon equals to delta L upon L. Now next comes shear stress and shear strain. So when a body is subject to two equal and opposite forces acting parallelly and tangentially across the section, as shown in figure A, it tends to shear off the body as shown in figure B. So this type of force is called as shear force, and stress induced is known as shear stress. The corresponding strain is known as shear strain. So when the body is trying to slice off, so this slicing action is called as shear stress. It's shear stress induced, and the load is shear load. So this resistance, as shear resistance per unit area, is known as shear stress and denoted by tau. Formula is tau. Shear stress is denoted by tau, and it is also shear stress or shear load upon shear area, P by A. So shear stress tau is P by A. Shear strain. So as you can see, a rectangular block ABCD with height h with length L, and shear load at acting opposite direction above and below. As you can see, arrows up, arrow P above, below are opposite directions. So arrow P moves to the right side, causing an angular deflection, that is pi, to a length of delta L at the top, the height h. So let the transverse horizontal displacement, so the horizontal displacement of will be delta L, the height to be h, and the shear strain is pi. So pi is transverse displacement upon the distance between the two faces, h, height of the block, so that is delta L by h. The shear strain pi is delta L by h. So these were the different types of stress. So other stresses, bearing stress, bending stress, and torsion stress, we will discuss in the upcoming modules. So right now, so these three stresses are very important, that is tensile stress, shear compressive stress, and shear stress. Tensile means the pulling stress, tensile strain means the pulling strain. Formula remains same, sigma is P by A, tensile strain epsilon is delta L by L, and compressive stress is pushing stress trying to compress, so formula is same, sigma is P by A, the strain epsilon is delta L by L. Shear stress is the slicing stress force, shear stress is shear stress. Shear strain is the shear stress given by tau equals to P by A. Shear strain is angular deflection, and angular transverse displacement, so pi is delta L by h.